Hello Bobcats. In this video we will be doing practice problems from the PowerPoint on gas laws. And you can print this sheet out from the Canvas site under Gas Law Resources. It's in the section where you can also find Gas's PowerPoint. It's right underneath that. And it'll be called Gas Law PowerPoint Practice Problems, and it's actually practice problems number 1. So let's start with Boyles Law. Now, Boyles Law, remember, is P1 V1 is equal to P2 V2. So what we're looking at is that the pressure and volume are inversely related to each other, meaning that if you increase one, you have to decrease the other. They're opposite of each other. So let's go through this problem. And the very first thing you should always do when you're doing gas law problems is identify all the variables. So in this case, as I read this, I have 3.5 liter sample of hydrogen gas, has a pressure of 0.50 atmospheres. What is the volume if its pressure is increased to 1.5 atmospheres at constant temperature? So my first variable I have is volume 1. So volume 1 is 3.50 liters. This is the pressure, the initial pressures. That's P1, and that is 0.750 atmospheres. Now as I go through this, it's asking for what volume, so that would be volume 2. We don't know what volume 2 is. That's what we're looking for. And if it's at a new pressure that has been increased, so the pressure 2 has increased from increased to 1.50 atmospheres. So let's make a quick prediction. If we know that they're inversely related, if I increase the pressure, then my answer should be a decreased volume. So when you do problems, we should also always write the original equation. In this case, I have already written it, but I'll write it again. P1 V1 equals P2 V2. And I need to isolate for V2. So I need to find that variable. And to do that, I would divide both sides by P2. So then you would write the rearranged equation. So that would be volume 2 is equal to P1 V1 divided by P2, because I divide P2 on both sides. And then after that, I would just substitute and solve, or in my case, you would say plug and chug. So in this case, we have P1, that's 0.750 atmospheres, and I'm going to use the dimensional analysis format because I like to make sure I have all my units taken care of. So again, that's a multiplication line. So that's P1 times V1, and V1 is 3.50 liters. And then I need to write P2 on the bottom, so that's going to be 1.50 atmospheres. Okay, now the atmospheres cancel, and when I multiply and then divide, so you multiply this times this divided by this. Don't need any parentheses or anything. So that'd be 1.75 liters is the answer. Again, let's check and see. We went from 3.5 to 1.75. It did decrease, so that works. If you're having a hard time seeing the dimensional analysis format, remember this is just P1 V1 over P2. So that's a simple Boyles Law problem. Let's do the next one, which would be Charles Law. Now Charles Law looks at temperature and volume. It looks at temperature and volume. And remember, temperature and volume are directly related. In other words, if I increase the temperature, I have to increase the volume in order to keep a constant pressure. And there's the term constant pressure. We're trying to keep constant pressure. So let's identify our variables. First, I have a 678 milliliter sample of a gas, helium gas. And its initial temperature is 0 degrees Celsius. is heated at a constant pressure. If the final volume, so that's my new volume, is 0.896 liters, what is the final temperature in degrees Celsius? Now, right away I notice I have milliliters and liters, so I have to have the same unit. In this case, I'm going to convert everything to liters. So volume 1, that's this one, volume 1 is equal to 0.678 liters. The temperature, now remember, this is very, very, very important. It's temperature 1, not temperature initial. Temperature 1, the temperature 1, you have to convert to Kelvin. Always, always convert temperature to Kelvin when you're dealing with gases. So that'd be 0 plus 273, so that's really 273 Kelvin. That's my temperature 1. What if the final volume, so V2, is equal to 0.896 liters? What is the final temperature? T2. Now remember, that's T1 up there. I accidentally messed up. And so that's T2. We do not know what it is. First we have to find it in Kelvin, and then we will convert it back to Celsius. So the equation is V1 over T1 equals V2 over T2. And I need to isolate for T2. So anytime I have a denominator, the first thing I want to do is try to get the denominators to become numerators. So the easiest way to do that is to cross multiply. So that would be V1 times T2. So V1 times T2 is equal to V2 times T1. V2 times T1. And then I want this by itself, so I'm going to divide both sides by V1. So T2 is equal to V2 T1 divided by V1. Now, so when I plug into those numbers, I will get T2 is equal to, now remember, V2 right here, V2 is 0.896 liters, and T1 was 273 Kelvin, and V1 is 0.678 liters. Now liters cancel, so that gives me a Kelvin temperature. Now when I do this, we're going to get 361 Kelvin when I take 0.896 times 273 divided by 0.678. Now, does this make sense? Remember, volume and temperature are directly related. So that if I look at it, my volume went up. I increased the volume. That means my temperature should also increase. And I went from 273 to 361. It did increase. So that's correct. The next thing is we have to convert it to Celsius. So now we need to subtract 273. And so the temperature in Celsius is going to be 88 degrees Celsius. So that's Charles' law, in which we're looking at volume and temperature, and they are both directly related to each other. The next law is Avogadros Law. And Avogadros Law looks at the volume and the number of moles of a gas. So let's look at Avogadros Law here. Now, in this case, let's write out our variables. And by the way, I should mention that, remember, Avogadros Law states that the volume is directly related to the number of moles. So if you increase the volume in the number of moles, you increase the volume. If you increase one, you have to increase the other. So if I look at, we have a sample that's this volume, so that's going to be V1. V1 is equal to 12.2 liters. Is containing a 0.50 moles of oxygen gas at a pressure of 1 atmosphere and a temperature of 25 degrees. If all of the O2 gas were converted to ozone at the same temperature and pressure, so this means that the temperature and pressure is held constant. So we're really looking at the number of moles. So N1 is this, 0.50 moles. Now, we're looking for what would be the volume, V2. That's what we need to know in liters. But we have to find the N2 also, because I've got two variables missing. Now, if you look at this, we're going to have to do a reaction, because what this says is that the O2 is completely converted to O3. So if I look at the reaction for this, we would say O2 converts completely to O3. And I need to balance it. And so there's a 2 and a 3, so that means I need 3 moles of oxygen here. It goes to 2 moles of oxygen there. Now let's do some thinking real quick. Remember that the moles and the number of the volume are directly related. So in this case I went from 3 moles to 2 moles, so that's a decrease, so my volume should decrease. But I still don't have the number of moles yet. That's just a ratio of 3 to 2. So if we look at this, we know that we have 0.50 moles of O2, and to get the number of moles of O3 I have to do the mole-mole ratio from the reaction. So it's a 3 to 2 ratio. So I do 3 moles of O2 for every 2 moles of O3 produced. And when I multiply 0.5 times 2 is 1, 1 divided by 3, that's 0.33 moles of gas. In this case O3, but it's really just we're worried about a gas because they're both gases. So now my N2 is 0.33 moles. So I did decrease from a half a mole to a third of a mole. Now let's write the equation. We said that they're directly related, so that means that, and let me do it in a different color just so I can show you what, the equation. So that's volume 1 over N1, that's a direct relationship, is equal to volume 2 over number of moles 2, or N2. Now I need to isolate for volume 2, but I've got to get rid of the denominators first, so cross multiply. So volume 2 times N1, so that's going to be V2 N1 is equal to V1 N2. And then, if you'll notice here, we're looking for this. So I got to identify or isolate that, so I divide both sides by N1. So V2 is equal to V1 N2 over N1. And when I put the numbers in, or plug and chug, we'll get V1 is 12.2 liters. I drew the long line a little too long. And then N2 is the 0.33 moles. Maybe I didn't. And then N1, which is on the bottom, is 0.50 moles. Moles cancel, and so I get, when I multiply, I get 8.1 liters. So it did decrease, so it makes sense. Now, again, if you're having trouble, remember it's V1 over N2, so there's V1 times N2, that's N2 divided by N1. So even though I'm not showing parentheses and everything like you're used to, my dimensional analysis works. I need to identify that up here also. So remember, this is going to be, if I look at the equation here, this is V2 T1 over V1. So it's still the same equation. Now because the moles are a little bit more involved, let's try another example of Avogadros Law. Now, so here I have a sample of, here I have a sample containing 22 grams of gaseous carbon dioxide, and it occupies a volume, so there's my volume, of 15.3 liters. What is the new volume? What would the new volume be if you have an additional 15 grams of carbon dioxide with no change in temperature and pressure? So we're holding temperature and pressure constant. Now I don't have any moles here, but we know that if I have a mass, I can convert any mass to moles using molar mass. So the mass, 22 grams, and it's carbon dioxide, so 1 mole of carbon dioxide has a mass of 44.01 grams. Now remember, that's 2 times 16, that's 32, plus 12.01, that makes it 44.01. So I have, let me get a calculator, I have 22, oh it should be simple, 22 divided by 44.01, that comes out really to 0.500, I'm going to go 3 sig figs because that's what I have in each of these, moles. That is N1. Now N2 I've added, so it's 22 plus 15. So N2 really, it starts out with 37.0 grams of carbon dioxide, and we know that 1 mole of carbon dioxide is 44.01 grams, and so that's 37 divided by 44.01. That comes out to be 0.841 moles, and that is the N2. So I've identified N1, N2. We know that V1 is equal to 15.3 liters. That's right here. And then we want to know what is the new volume. So we're looking for V2, question mark. Again, they're directly related, so it's V1 over N1 equals V2 over N2. I'm looking for V2, so I'm going to cross multiply again first to get rid of the denominator. So that's V2 N1 is equal to V1 times N2. Now I'm looking for V2, so I divide by N1 on both sides. So V2 is equal to V1 N2 over N1. I'll substitute. Excuse me, I had to sneeze. Substitute and solve, or plug and chug. So V1, 15.3 liters. N2, that is the second one, so that's 0.841 moles over N1, which is 0.500 moles. And when I calculate this one, 0.841 times 15.3 divided by 0.5, enter, I get 25.7 liters of CO2. Does that make sense? So we went from 0.5 to 0.841. That is an increase in moles, so I should increase the volume, and it did. It went from 15.3 to 25.7. You should always evaluate your answers to see if they make sense. Now let's see if I can fix this. It looks a little crooked there. Okay, let's go on. We still have a couple more problems to do, because the next gas law is combined gas law and then the ideal gas law. So there's the 3 basic gas laws. Boyles Law, which is P1V1 equals P1V1 equals P2V2. Slow down. They're direct inversely related. If you multiply them and they have to equal on each side and you're multiplying, it is inverse. If you increase one, you have to decrease the other. Charles' law is V1 over T1 equals V2 over T2. So we're looking at the relationship between volume and temperature, and they are directly related. As if you have them as numerator and denominator, you can know they're directly related when they have to equal on both sides. And then, of course, volume and number of moles is also directly related, Avogadros Law. Now, remember in the last lecture, we talked about how we can actually combine these three gas laws and just remember one equation. So let's do the next problem. And the next problem would be a combined gas law problem. So let's look at combined gas laws. Now, again, it's very, very important to identify all your variables first. And so in this case, we are starting out with a 17.3 milliliter sample of argon gas. It was originally at 0 degrees Celsius. Now remember, we've got to change Celsius to Kelvin, and it's at 1 atmosphere. What is wrong with something's not working out right. Oh well, we'll just go with it right now. Okay. And if the final volume, so that's going to be V2 is, oh no, this is V2, so that's the final volume. So let's go ahead and start identifying. We've got V1 is equal to 17.3 milliliters. T1 is 273 Kelvin. Remember, we don't want Celsius, we want Kelvin, so just add 273. Then we have P1, so that is 1.00 atmospheres. Then we go on, if the final volume is, so that's V2, 10.9 milliliters. The final pressure is 670 torr, so P2 is 678 torr. Well, I realized right away my atmospheres and torr pressure units do not match, so I got to convert. And to do that, I'm going to convert torr to atmospheres. 1 atmosphere is equal to 760 torr. So when I divide, my P2 is going to be 0.892 atmospheres. So that's P2. And it says, what is the final temperature? So the final temperature, T2, we're going to find it in Kelvin first, because we have to, and then we'll convert it to Celsius, because it says, what is it in Celsius? So the combined gas law equation is P1V1 over N1T1 equals P2V2 over N2T2. Now remember, let's just review real quick. P1 times V1 over is equal to P2V2. That's Boyles Law. Then if we took volume divided by temperature equals volume divided by temperature, that's Charles' Law. And then volume divided by number of moles, volume divided by number of moles, that is Avogadros Law. So we've combined them. Now the next thing I would do is I would try to figure out if anything was held constant. And the easiest way to do that is one of the variables is not mentioned over here that I've filled out, and that's N, the number of moles. So I cancel or cross that out. So I don't need to look at that. So in this case, remember, we're looking for temperature 2, so I have to isolate for T2, that one. So anytime I have a denominator, I want to cross multiply. So in this case, I'm going to go P1V1 times T2. Remember, N is gone. So that's P1V1 T2 is equal to P2V2 times T1. P2V2 times T1. Now, again, don't forget, we're isolating for T2. So I need to divide both sides by P1V1. So T2 is equal to P2 times V2 times T1, P2 V2 T1, all over P1 V1. Now I'm going to plug and chug, or substitute and solve. P2, That was 0.892 atmospheres. V2 was 10.9 milliliters. T1 was 273 Kelvin. Then I'm on the bottom, and so the bottom is P1 is 1.00 atmospheres. I put it in the same column so I can cancel. Makes it easier to see. And then the next one was V1, and that is 17.3 milliliters. And the milliliters cancel. So when I multiply across the top and then divide, so that'd be 0.892 times 10.9 times 273 divided by 1 divided by 17.3. That's how I'd put it in the calculator. We get a temperature 2 of 153 Kelvin. Now remember, we want it in Celsius, so what do I have to do? I have to subtract 273, and so my answer is a negative 120 degrees Celsius. And I put the decimal so you know that it's 3 significant figures, because everything's in 3 sig figs. So that's the combined gas law. The last gas law is the ideal gas law. An ideal gas law, the way I know I'm working with an ideal gas law and not a combined or one of the other gas laws, is that ideal only includes one of the variables. So I only have one atmosphere, or one temperature, or one number of moles. Up here you'll notice you've got 2 volumes, I've got 2 pressures. So anytime I have double of a variable, I'm going to use the combined gas law, or if you can remember, Boyles gas law, or Charles gas law, or Avogadros gas law. But that's only when you have 2 of the same variable. When you only have 1 of the variables, we're going to use ideal gas law. And a really important thing to remember about ideal gas law is that we have a constant, and the constant, R, gas law constant, is 0.0821 liters times atmospheres over mole Kelvin. And it's very important to remember these units, because we got to make all of our units match these 4. So as I go through the problem and do the problem, now at this point I usually just write the variable above the number. So calculate the volume. So we want to know what the volume is. When we have 1.63 moles, and that's going to be in carbon dioxide gas at this temperature, that's T, and then we have this pressure. Now I look, and I've got moles, I've got Kelvin, and I've got atmosphere, so I have the right units. So now I'm going to write the gas law. PV equals nRT, Pivnert. That's a nickname, by the way, Pivnert. It's really called the ideal gas law. And then I am looking for volume, so I've got to isolate volume, so that's divide both sides by P. So V is equal to nRT over P, and then I substitute and solve. I'm going to use my dimensional analysis format, and so this is N, which is 1.63 moles carbon dioxide, R, which we know is going to be 0.0821, and I put it on top, liters atmospheres over mole Kelvin. And we know right away that the moles cancel. Then we're going to have temperature, so that's going to be 295 Kelvin. Kelvin cancels. Over pressure, which is 1.14 atmospheres. And the atmospheres cancel. And if you're having a hard time seeing the equation, remember it's N R T, so that's N times R times T divided by P. And when I multiply and divide, I get 34.6